Hey everybody, good evening and welcome. This is Obi-Wan Pez for Simplex Pachinko. We are going to be doing some more math tonight. And in particular, we're going to look at cracking the GRE math test. And we're probably going to finish up the trigonometry section and then move on to calculus. And as always, if anybody has any other questions, feel free to drop them in to the chat or over to Penn Center's Discord, which is kind of our central repository for questions and getting help from multiple sources. So we do tend to like to turn you to multiple individuals and say, hey, look, get help from a number of different sources and see what you like as far as your personal explanation of a particular concept. Usually works out better if you've got more opinions on how to do a math problem. So the Elements Discord is going to be here. Again, this is Penn Center's called The Elements. And just out of curiosity. Oh. And then we also have Zach, who is also known as E to the 2i pi, who is live right now as far as I know. So feel free and head on over there if you would like to talk with Zach, and you can always stop over at his Discord as well. Although I will say, it's usually better if you are known to that particular stream. It's just that I don't have my own Discord. I don't really care to make one available. I have to manage all of that. Sorry. At any rate, so we're going to be working on, like I said, our trigonometry stuff from the last few classes that we've had here, the last few days that we've been talking about mathy type stuff. I did want to get, a solid understanding of how the basics worked, so that is kind of how I'm running this whole thing in the first place. Is that we are talking about concepts first, and then we'll work on individual problems and things like that, and how do you complete this problem, and also if you're actually taking the GRE, how would you, for instance, complete a particular question in the fastest way possible, because you don't have a whole lot of time when you're doing this in a testing environment. So we figured out all of the individual formulas that we were going to use: addition, subtraction, double angle, half angle, all that good stuff. We did not discuss the tangent of alpha plus or minus beta, because for the most part, like, my school never used it. We found it to be just kind of complicating everything, and essentially, why should we bother? However, in the spirit of attempting to do, attempted to give you the most complete picture, we will look at this and say, okay, our tangent of alpha over beta, nope, our tangent of alpha plus or minus beta is going to be the sine of alpha plus or minus beta. I need to turn off this other thing that's eating my processing power. Okay, divided by the cosine of alpha plus or minus beta. Which is, the sine of alpha plus or minus beta is the sine of alpha times the cosine of beta, plus or minus, same sign, different functions. And here we have the cosine of alpha times the sine of beta. For the cosine, the like functions are stuck together. So cosine alpha, cosine beta. But we have unlike signs. So minus plus instead of plus minus. Sine alpha, sine beta. Okay. Now in this particular case, what we might want is not to deal with this in terms of sines and cosines, but rather in terms of tangents. So if we could have this in terms of tangents, that'd be really nice. So what we can do is divide by each of the terms that'll get us a tangent. So if we take the cosine of alpha and divide it from every term, then where it doesn't get rid of the cosine of alpha, it will create a tangent of alpha. And also, we apply the same logic to beta. So anywhere that if we divide by the cosine of beta everywhere, then either we get rid of the cosine of beta or we create a tangent of beta. So in the first term, we've got cosine of beta. In the second term, we've got cosine of alpha. In the third term, down at the bottom, we've got the cosine of alpha, and in the and also the cosine of beta. This leaves a 1 behind, as do all the rest of the divisions, but we won't belabor that particular point. And then we've got the sine of alpha over cosine of alpha, which is going to get us a tangent of alpha times 1 plus or minus. Sine of beta over cosine of beta is going to be tangent of beta. Okay, divided by 1 minus plus. This is the tangent of alpha times the tangent of beta. Now this is probably among the super simplest formulae that exist anywhere within trig, or the proofs of formulas, because we're coming at this from the point of view of already having the sines and cosines, sums and differences formulas. And so here we're just saying, well, if we divide by all these terms, we can get tangents. And all of these terms either have tangents or don't. In terms of, well, the only term that doesn't have tangents at all is a 1. So that's nice and simple. Okay, and then if we want to take this as tangent of 2 theta, for example, we'll stick with alpha just to make it slightly easier. This means that, again, we have the tangent of alpha plus alpha. Right, let alpha equal beta, and either we get the tangent of 0, which we can just double check, or we get the tangent of 2 alpha, which now we can come up with a new formula. So here, tangent of 0, alpha minus alpha, is going to be the tangent of alpha minus the tangent of alpha over 1 minus plus tangent squared alpha. So here up top we get a 0, which means that overall the whole values can be 0, which is what the tangent of 0 is. Okay, then if we go with the tangent of 2 alpha instead, then what we get is the tangent of alpha plus or minus. In this case, right, this is plus, not minus. And over here, this was a minus up top, so it's a plus down bottom. 1 plus tangent squared alpha, which is secant squared alpha, actually, in the denominator, but we don't need that. So tangent of alpha plus tangent of alpha, so those are going to combine, divided by 1 minus tangent alpha times tangent alpha, which again, we end up with a 2 tangent alpha up top and a 1 minus tangent squared alpha down bottom. There's a reason why I wrote this on the opposite line, or the next line down. Alright, so the tangent of 2 alpha is equal to 2 times the tangent of alpha divided by 1 minus tangent squared alpha. And then that also means that we should be able to come up with a formula for the tangent of alpha. Now, at this exact moment in time, we've got kind of a difficult prospect here. I'm going to... Right, so this is going to be the tangent of 2 alpha. Multiplied by 1 minus tangent squared alpha is equal to 2 tangent alpha. So the real question is here, how do we get the tangent to combine those terms and put them together? So I think the only way that we can even attempt at doing this is by multiplying all this out. So tangent 2 alpha minus tangent 2 alpha times tangent squared alpha minus 2 tangent alpha is equal to 0. And I mean, technically this is a quadratic on tangent of alpha. It's kind of gross. Alternatively, we do have something that looks like if we were to shift everything to the other side, ax squared plus 2x minus a is equal to 0. Yeah. For which x is going to be equal to, this is negative 2 plus or minus the square root of 2 squared minus 4 times a times c is negative a, all divided by 2a. X is equal to negative 2 plus or minus square root of 4 minus 4a squared. No, plus 4 plus 4a squared, which can also be 4 times 1 plus a squared. All over 2a. The 2's are going to divide out from all terms. So this is a 2 that comes out. And we've got a 2 over 2 times a. This is now 2 times the quantity negative 1 plus or minus square root of 1 plus a squared. So the 2's are gone. That's not what I wanted. X equals negative 1 plus or minus square root of 1 plus a squared, all divided by a. Okay, so this is tangent of alpha is equal to negative 1 plus or minus square root of, that's kind of weird, 1 plus tangent squared 2 alpha all over tangent of 2 alpha. Right? Just to make sure, right? Tangent squared plus 1 is equal to secant squared. Cool. So now that we have this, we can actually say that this square root in the numerator becomes secant squared of 2 alpha all over tangent of 2 alpha. Negative 1 plus or minus secant. Technically, that should be the absolute value. Yeah. Of 2 alpha. All over tangent of 2 alpha. And I can be a huge pain in the ass about this. I want to know. Nice. We get a square wave. So we could make it in terms of cosine, but that would end up not being particularly nice. That would also make it a sine of 2 alpha on the bottom. So that's interesting. What does this say? Tangent of... Wait. What was I doing? Let's just double check. We wanted to know... Okay, we wanted to know what the half angle identity is going to be. So I was trying to take this in the direction that... all of our 2 alphas could become theta, and then our angle on the outside, alpha, could become theta over 2. So this gets us a... right, this gets us a version which is dependent only on 2 alphas as our variable, which is what we do want. But interesting. Okay, so it does actually. Okay, now I don't see it. It may actually be easier to go the other route that I did not use, which is to say that the tangent of alpha over 2, theta over 2, whatever you want to call it, right, sine of theta over 2 divided by cosine of theta over 2. Okay, which was the square root of and so both of these are plus or minus, but realistically it just depends on what quadrant you're in. So here we have sine is 1 minus cosine of theta. all over 2. Cosine of theta over 2 is the square root of 1 plus cosine of theta all over 2. And in this case, right, both of these pieces will join up together. Our division by 2 goes away in both cases, or divides out from each. And here we get 1 minus cosine of theta over 1 plus cosine of theta. Right, multiply both top and bottom by 2 equals here we can multiply both top and bottom inside of the square root by 1. No, we want the conjugate. So 1 minus cosine theta divided by 1 minus cosine theta. Now, why on earth would I want that? Well, you'll find out in just a minute. Right, the top becomes 1 minus 2 cosine theta plus cosine squared theta. And the bottom ends up becoming 1 plus cosine theta minus cosine theta minus cosine squared theta. The denominator becomes sine squared of theta. And the numerator is 1 minus cosine of theta parentheses squared, or 1 minus 2 cosine theta plus cosine squared theta. I'm not seeing an easy way out of this one, so especially since sine should be, according to this, in the numerator. It's a little bit odd to me. Right, I did sine over cosine. No, I didn't. It should be cosine squared theta. Ah. Yep. Alright, get the conjugate of the denominator so that we can get this. So that's going to be right, 1 minus cosine squared theta parentheses squared is going to be sine squared of theta parentheses squared. And down the bottom, Down the bottom, we're going to get 1 plus cosine squared theta times sine squared theta. Sine squared theta. Plus cosine squared theta. I don't want to have it as like in terms of I, because that would just be horrible. So what we should be getting is just 1 plus cosine theta in the denominator. Unfortunately, we've got a few other items that are in the way. And we're not just allowed to, clear stuff because we feel like it. So oh no, it is. Man, I had it right the first time. No, right, because the power is where the... Man, we're having a day. I was right the first time. Oy. All right. Hey everybody, good evening and welcome. My name is Obi-Wan Pez. This is in Simplex Pachinko. Right now we're looking at the half-angle formula for tangent and trying to derive it. So, that's fun. I kid. Ah. Thank you, Zach. Thank you for bringing everybody in, and hope you all had a great night. Anybody who doesn't know Zach, this is the one I was talking about earlier. All good things. There you go. So if anybody has not yet followed Zach, go for it. I mean, yes, you all know Zach. That's mostly for people who are here on demand later. What'd you get up to tonight? Okay, so it essentially uses vector analysis to do this one. Mischief, awesome. Philosophy of teaching, very nice. One of my more favorites. So, not really. There is a particular form of the half-angle identity for tangent where you end up getting sine of theta over 1 plus cosine theta. And that's it. Over here, I had attempted to do that. It ended up not quite right. In fact, this appears to be almost upside down. So that seems pretty weird. We'd attempted to say here in blue, if we have tangent of 2 theta is equal to 2 tangent theta over 1 minus tangent squared theta, then we can rearrange everything. The tangent is then going to be a quadratic. So tangent of alpha is going to be x in this thing. And then the tangent of 2 alpha ends up becoming a, which is constant, only it's not really, which also kind of bothers me. But I was trying to see if there was any way to, at the very least, be able to come up with some reasonable method how all this works. do the other one. Okay, so if I go that way, right? Oh. Yep. Oi. Thank you. Alpha. No, that's theta. Okay. All right. Thank you. Whew. I don't know if it's just been a sleepy kind of day in general or what, but it is also rather warm in here at the moment. So glad that I decided to change to shorts, because I would probably be melting. There is also another... There's also a bunch of sum to product, product to sum formulas and things like that, but we never use them just because they got rather large and ridiculous. Double angle using geometry. Yeah. Oh, the tangent. I see. I think actually Zach had that one yesterday. Or Monday. Could be wrong. Didn't get it here, but... Alright, now I'm curious. I won't give it all away. So if we go with alpha 2 alpha, right, this is going to get us a tangent. Whose tangent is over here. Yay. Could just choose a different angle, but you know what? It's fine. This is the secant of alpha here. This is the tangent of alpha here. And we've got smaller versions of the same. This is our cosine alpha. This is our sine alpha. This is secant 2 alpha, tangent 2 alpha. Cosine 2 alpha, sine 2 alpha. And naturally those are 1s. If it isn't, this is really close to being a kite. I think it should be. Not that that matters anything necessarily, but you know. Minus 2 alpha, and then if we have 180 minus 2 alpha plus 90, which we're subtracting from 180, then that goes away. And this is going to be 2 alpha minus 90. Is our reference angle. Meant from known angles. Okay, fair. Not to say that this gets us anywhere necessarily, but Yeah, you know. Yeah. I don't think there's anything that we can guarantee with those particular points. The only other thing we might be able to do... No, we don't really want, like, the distance, right? Because that was good for alpha minus beta, because all we were doing was taking a fixed angle and then rotating that fixed angle. So the distance between our two terminal points was angle invariant. That's why it was easy to then relate those two things together. Yeah, we'll take a look. Do, 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 do. Right, so if we go with If we go with 2 alpha here, you're saying draw in, right, it is isosceles because radii. This is a particular distance, we don't know what it is, but that's fine. And then we're saying here this is going to be half okay, wait, hang on. Not there. Central. The central angle is the thing that we're... Okay, let's redo some of this. It's not here. What we need to do then is to create a central angle that encompasses 2 alpha. Or, sorry, that is it. Ah, come on. So that's got to be from here to there. So that is going to be alpha. However, that does not guarantee that we have an isosceles triangle. Oh, it does. Yep. Okay. I'm looking at it from the wrong perspective, so that's why. There's a 1 there, right, which is going to guarantee that this is also alpha. Right, and then this is going to be 180 minus 2 alpha. Okay, that's better. And also me choosing a perspective that's strange because it's off to it's in a different quadrant, right? How dare I choose something in a different quadrant? Oh, did I miss ads again? I didn't have them up because I was looking at a different page. Okay, 2 minutes. Alrighty. And we're going to redeem good form. Because of course. I think we want to do the other blue belt form. So that one is called Keybon 4. And starts with let's see. Starts with snapping together, bow in, all that good stuff. Starts with attention, which gets us to this point, and we snap whatever it is. If we're grabbing something, we're basically just tugging it to our hip, and then we kind of go oh, you fall into it. Yeah, it's a reinforced block, and we're kind of awkwardly stepped like this. So then this is not a side eye, so we don't go back over here. This one goes up, and then tension's down. And then from here, look to the right, and we've got 3 moves. So this is I want to say pierce. Oops, that way. Pierce, elbow smash, and then we ball up the right fist behind our arm and do a double strike, one up, one down. And from here, this is going to turn back around the other way, and it's a down block here and also a down strike here at the same time. Same on the other side. And back here, after 3, we go into let's see, this is where it gets weird. So with our right hand back, we go to do a right chongle punch, but then we notice that somebody's trying to hit us, so we go, oh crap, and we do like a right punch followed by an up block. And we're in this like elongated stance and turn sort of 45 degrees outward at the same time. And then we go back to a left punch, and then same here. Now we're like kind of 45 degrees that way-ish. More like 90. And then, or is it the other way? And then we gotta come back. That might be it, actually. So we go right side first, left side second, and then we bring it back, and we do an up block with the left hand and like a strike with the right hand, and then come back around and do a back fist with the right hand. And then that's the part I forget. Overall, pretty decent memory of that one. My notes are such crap. It's just all make it up. Not quite make it up, but oh, nope, that's Neon Chi. Oh, yeah, it was there. Okay. Change. Right, left. Change right foot to Changul. Reverse punch up block. Left, reverse punch up block. Twist Changul face right. Up block and pierce, yeah, I did that. Step right into cat stance. Side wrap. Left hand support, yeah, okay. Yeah, okay. So once we get here, actually, that's another block this way. And then once we get there, we step left, right, and center with Fugo Sudo. And then step back. Tension. And once without reading. Nope. I was right. That's it. That was wrong before. So from here we do a left, right, pierce, followed by a left, followed by head smash. And that's when we do the wrap that way. Okay. 1, 2, 3. Blue belt. All right. So, math night. Thanks anybody who stuck around. And work on rest of this bit here. If anybody does have any questions about other mathematics that we are not doing, feel free to ask either in Discord or in chat, and we will answer accordingly. Okay, so with 2 alpha, now we've got here all of our, excuse me. So if we have alpha on those 2 locations, we have 1 there. 180 minus 2 alpha is our other angle. Now we want to know right, 2 alpha is the entire central angle. Alpha is just going to be the outside angle. So it has to be half as much. And then from here, we have, again, this is going to be like cosine of 2 alpha. It's going to be sine of 2 alpha. This is going to be 1 minus cosine of 2 alpha. Oh, look at that. And it's right triangle trigonometry. So that one's super easy. This is tangent of 2 alpha we want to get the tangent of 2 alpha based on stuff that involves alpha only. Uh-huh. How would we then scale that? Okay. So our radius here is going to be the distance there. Oh, but it's tangents anyway, so like, who cares? We're gonna... Okay. Tangent of 2 alpha is going to be equal to the sine of 2 alpha over the cosine of 2 alpha. We know that. It can also be... which? Okay. Okay. Sine of single alpha is going to be equal to the sine of 2 alpha over d, and the cosine of alpha is going to be equal to 1 minus cosine of 2 alpha, also over d. So when we correctly modify this, should bring over the other stuff, solve for sine and cosine of 2 alpha, in theory. Sine of 2 alpha is equal to d times sine of alpha, and cosine of 2 alpha is equal to, those are going to swap positions. D is going to be on the cosine of alpha, so that's 1 minus d cosine alpha. Or, and hear me out, right? Or, this is going to create the same right triangle here. So we're not relating it to D because that is dependent upon other stuff. But if we do it this way, this would be the tangent of 2 alpha Okay, and then the heights, the legs of the triangles could be something like tangent of 2 alpha. It's going to be the short side. That's a terrible idea. That's our known angle, 180 minus 2 alpha. So it's that triangle, it's that triangle. So the one opposite that angle is tangent 2 theta, which is related to sine of 2 alpha. Okay, and that relation should be equal to 1, the length of the other leg of the big triangle, divided by the length of the other leg of the small. That's cosine of 2 alpha. Hey, Famish, how's it going? Of course, that's right. Oh. Okay, but hang on. We want to relate this instead, since we already know that that's true. That's a definition. Is there another way to relate this specifically to units involving just alpha? So, like, we've got the tangent of alpha is equal to, and that gives us a, oh, yes, that is exactly what I want. I think I was forgetting what I was trying to solve for. Oh. All right. Thank you, Dissa, for for not entirely just making fun of me here. So, yeah, worked out nicely. Working on some graded projects, yep. Textbook and looking stuff up, yeah. So, this is the half angle for the tangent function. So if we wanted to go for the figuring out what the tangent of half of a particular angle is going to be based on the angle itself and its trig functions, then we can use this formula that I've just circled. Right, the tangent of our half angle is going to be equal to the sine of the original angle divided by 1 minus cosine of the original angle. I was having a really hard time seeing it, even though it was literally just right in front of me the entire time. And then I went to an unfortunately timed ad break, and I came back and nobody was here. So, we are hashtag not sponsored tonight by Cocoa Wonderland by Thornbridge Brewing. Has a nice kind of reddy color as I shine a light through it. Ooh. Chocolate porter. Almost got like a marshmallowy. Yeah. It is beer. It is a... Usually they just are doing craft stuff. But this one does contain lactose. Yep. Malted barley, wheat, Lactose. Oh, that's not all the instructions or ingredients. Alright, well, whatever. Alright, so we got the half angle for tangent. Again, thank you to Dissa for turning my attention to the easy way to solve that one, even if I didn't necessarily get it right away. Right here we also have the algebraic method of solving it. This was going to be based on whatever quadrant you end up in, so the plus and the minus out front just kind of depended on like which quadrant you were in. I guess now that we have this here, right, our sine and our cosine, that kind of determines what the quadrant's going to be, so we wouldn't actually need it at this point. Yeah, this is really weird because I guess technically like it would be a plus minus but also an absolute value because we just took the square root of stuff that was squared. So because it's plus or minus and because we also have an absolute value, then it's going to end up either a plus or a minus. Again, depending on what quadrant theta over 2 is in and the tangent function. So it just ends up being whatever it's going to be. Okay. We also have... Yeah, this was my earlier attempt at trying to go with... if we start with the double angle formula, how do we get the single, or how do we get the half angle formula from the double angle formula? And we got really messy before I decided that was probably just going to call it quits there and trust that I was not going to actually be able to get that in that particular setup, unfortunately. Okay. In addition, right, express the following in simplest terms. Sine of 2 arctan x. Okay. So when we start talking about trigonometric functions, we also need to talk about their arc functions. So the arc is really asking for what angle do we get this ratio. So for instance, arc sine of 1, our answer is going to be pi over 2. Or 90 degrees if we're doing degrees, but most of the time we're not. So try to stick with it in radians as much as possible. So again, here, for what angle, we're going to give our answer, right? And then will we get whatever ratio it is? This particular sine ratio is 1. So for what angle do we get the ratio of 1? That's going to be pi, or for what angle for the sine function do we get a ratio of 1? That's going to be pi over 2. Now somebody could argue, what about 5 pi over 2, because that works as well. And then we'd say, okay, well, it only works on the first rotation in the first place. So we're going to limit our answers. Right, we're going to limit our answers. And then we got to say, in what way are we going to limit our answers? Because if we just say it's on theta goes from 0 to 2 pi, right, then we have to say, well, if we do that, then what is the arc sine of 1/2 going to be? And the problem with this is that the arc sine of 1/2, we get a 60-degree angle in quadrant 1, which is pi over 3. But we also get 2 pi over 3, which is a 60-degree angle in quadrant 2. And if you remember, this is a problem, right? This is not a function. So we can't include anything in quadrant 2 because those all repeat the values from quadrant 1. So we're not allowed to use any of the stuff in quadrant 2. But then the question is, like, how do we get stuff from quadrant, or how do we get negative values of our ratio? How do we plug those in? Where do we plug them in? Okay, well, it could be quadrants 3 and 4. But it'd be really awkward to plug in 3 after we just skipped 2. So can we plug in quadrant 3 immediately after skipping quadrant 2? Not really. It doesn't quite work that way. In theory, you could do it, but it'd be a pain because now we have two separate range spaces. So instead, well, what about quadrant 4 and then quadrant 1? Quadrant 4 leading into quadrant 1. Well, that's nice and smooth, right? Our sine function will go from -1 at the bottom at negative pi over 2, and then up through 0, and then up through a value of +1 at pi over 2. And then it can not exist after that, because now we've got, again, if we have more than one angle that's coming out, it's not going to be a function. So we have to limit our domain. Sorry, in this case, we have to limit our range for the arc sine function. So based on the sine function, right, what we want is, again, once we reach the maximum, we can't use all this stuff. And then, again, we could use the stuff down here, but then again, we'd have to skip quadrant 4, which would be the next one. Well, that's really awkward. Let's just skip quadrant 3 instead. And we include quadrant 4. And then we can't include quadrant 1 here. So I would argue let's not include quadrant 4 here either. Let's include quadrant 4 down. Oops. Wrong symbol. Let's include quadrant 4 down here. So now we have a connected space. We're using a continuous function. So from negative pi over 2 to pi over 2. Right, we have that continuous function. That looks pretty good. So we use theta is equal to arcsine of this ratio. So then what do we get for r, right? What do we get for our ratio? Well, our ratio can be anywhere from -1 to +1. And that's our independent variable for the inverse function, the arcsine. And theta is going to be our range for the arcsine function. Right, so then what do we do for, like, our cosine of our ratio being theta? Right? The arcsine, or arc cosine, looked like this. And we have the similar problem. We have minima down here, we have maxima up here. Oops. And again, we want to cover the entire area that goes between a maximum and a minimum, while including continuous function values, and we want to include, like, all the way from a ratio of +1 to -1. So for this, we're going to include everything from 0 up to pi over 2. Nope, that's pi. Everything from 0 to pi. Right, eliminate all this stuff, eliminate all that stuff. It's not going to work for us. We're only including the values between 0 and pi. That's going to be our range. Let's not do that right here. Theta is going to go from 0 to pi inclusive, and r is also going to go from -1 to 1 inclusive. So again, just like sketch a graph and then ask, what is the largest area that I can include, which ends up using all the values from -1 to 1 for our ratio. When we get to arctangent, it's a little bit different. Right, our tangent function ends up existing between -pi over 2 and pi over 2, and then repeats itself outside of that. So, quite honestly, just use that. It's all negative values going from -infinity up through 0, 0, and then positive values going to positive infinity once we start reaching toward pi over 2. This is all continuous. Let's just use that. Right, so this is theta is equal to arctangent of r ratio So here, theta is going to go between, oops, nope, not inclusive. Negative pi over 2 to pi over 2. And r, in this case, the ratio can be all real numbers, right? We can get any value that we want, negative infinity all the way up to positive infinity. The other two are a little bit weird. So when we get theta equals arc cotangent of r, right, we have to think about the original cotangent function. Cotangent has asymptotes on multiples of pi. So pi, negative pi, 2 pi, 3 pi, 4 pi, negative 2, negative 3, negative 4 pi. So all those values, whole multiples, integer multiples of pi, end up having asymptotes. Okay, and then we start with high values and then go negative. So here, in this case, theta goes from, we'll go 0 to pi. We keep it on the first rotation from 0 to 2 pi. And in this case, it stays continuous on that whole rotation. And again, our radius is going to be all real numbers. Right, if we want to go with theta equals arc secant of r, secant has cosines in the denominator, so whenever cosine is 0, that's where we end up having asymptotes. So that is going to be at pi over 2 and negative pi over 2. And a secant has its value at 1 when our theta is 0. And then that's going to go up from there, and up going in the other direction as well. And then we have downward ones as well. So you may see another problem here in that we have now discontinuity. So if we stick with just continuous stuff, then we end up with overlap, and then it's not a function anymore when we go to the arc-secant. A reminder that this is really a test of finding stuff, finding functions, or at least finding a space over which a function is one-to-one. Right? All of these functions are one-to-one over what space? We try to make it compact, meaning like as short of a distance as possible. And it's not really what it means, but it's close enough for our definitions. We're doing pre-calc. We want to keep it compact, so as little deviation as possible from like the main area, no spaces between stuff if we can help it. We want to make sure that it is Yup. We want to make it compact. We want to make it cover all possible values of the radius, or sorry, the ratio, while also including as compact and as nice values of theta as we possibly can. Now we've got a bit of a problem with our secant in that now this is no longer one-to-one in these places. So what we have to do is say, okay, we're going to eliminate all the duplicate stuff. Let's keep the stuff in the first quadrant, dump the stuff from the negative part. And in fact, since we just created a gap here, let's just dump all the negative stuff. In the positive direction, we have this stuff that starts at negative infinity down here, and then comes up until we reach pi, and then it starts going back down again. Now we've got duplicates on that side, so we don't want to include that either. So that means that here, we want to include very loosely, right, the entire space between 0 and pi, but we have to cut out pi over 2. Right, this is a legal way to say things. We want the interval between 0 and pi, except, so with the exception of this one singleton, pi over 2. Another way to say that would be to just say theta is going to go from 0 to pi over 2 open, union open pi over 2 to pi closed. We can go with either one of those. Right, and our radius, not radius, our ratio is, this is a little bit weird, right? So we've got numbers that go all the way from negative infinity up through -1 inclusive. And then there's a gap. So we've got to union this with stuff going from inclusive 1 up through infinity. Again, that's open because it's just going on forever. So our cotangent, our secant, our cosecant is the only other one that we haven't done. Right, arc cosecant of r. The regular secant function has cosecant. The regular cosecant function has zeros at x equals 0, and at x equals pi, and at x equals negative pi, so all of our whole multiples of pi again. Okay, and then again at all of our large values for, this is sine, be they positive or negative, end up with maxima and minima for the cosecant function, which then is going to get us somewhat informed as to what's happening with the arc cosecant function. So here, again, get rid of all this negative stuff that's well beyond, that's duplicating all the stuff between negative pi over 2 and 0, and similarly between all the stuff that is duplicating the items that go from 0 to pi over 2, namely from pi over 2 off to pi. Right, get rid of this too. So our theta is going to be, and again, we could do this as bracket negative pi over 2 to pi over 2, except 0, or bracket negative pi over 2 up to 0 open, union open 0 up to positive pi over 2, inclusive. And again, our ratio is going to go from negative infinity up to -1, inclusive, union, inclusive, closed, +1 through infinity, open. All right, with that, we said we want the sine of the arctangent, or 2 times the arctangent. Sine of 2 times the arctangent of x. So, the arctangent of x is telling us that this should be a ratio right, as we discussed from over there. So x is a ratio. It's x over 1, which is going to get us some theta when we look at the arctangent of that. So the arctangent as a whole is going to be an angle. And then we have the double angle, so 2 times that. And then we're doing the sine of something, so that's going to get us overall, right? The answer should be a ratio. Now, one thing that we can do is create a right triangle and say, let this be theta. And that means that the arctangent of x over 1 is going to get us theta. So what angle is this going to be? Well, x over 1 is not going to be a strict number, obviously. However, this does mean that we have the tangent is going to get us opposite over adjacent. That's an x, that's a 1. Right? So now we want to be able to double this angle and then figure out from here, what is our sine going to be? Because that's really what we want. But that's kind of a pain in the rear. So we're not going to do it 100% directly. What we're going to do is we're going to say this is a right angle, this is x, this is 1. This is theta. The sine of 2 theta is equal to twice the sine of theta times the cosine of theta. And in order to get the sine and cosine of theta, we also need the hypotenuse. So here, this is going to be a Pythagorean theorem. The hypotenuse squared, like c squared, is going to be equal to a squared plus b squared, which is 1 plus x squared. And then we take the square root of all of it because we want c, not c squared. So this means that we now have twice the sine of theta, given that diagram, is going to be x over square root 1 plus x squared. The cosine, according to that diagram, is 1 over the square root of 1 plus x squared, which is equal to 2x on top over 1 plus x squared on bottom. And that is it. Yep, cool. That is the sine, no, not there. Sine of 2 times arctan of x. Okay. Evaluate. Our cosine of 2 over the square root of 5 plus our cosine of our cosine of 3 over square root of 10. Well, we can do the same thing with this. See if there's any connection between the two. So if we have the arc cosine of 2 over the square root of 5, that's going to get us 2 down here and root 5 up there. That's going to be our, let's call it alpha, right angle. And arc cosine of 3 over root 10 is going to be 3 here, root 10 there. We'll call that one beta. Yep. Okay. So if we want the sum of two angles whose cosines are given, okay, so this is alpha plus beta is equal to the arc cosine of, because the cosine of alpha plus beta is going to be equal to the arc cosine of cosine alpha cosine beta minus sine alpha sine beta. May not actually do anything. Ads are about to start, so I'll probably run that and then just sit for a minute and continue to figure this out. So follow along, all that good stuff. I will see you in 3 minutes. Thank you so much, everybody, for coming, and we'll be right back.
You've been talking about patience, hoping forever
Well, it worked. So, made a little diagram here. We said that our we said our alpha is going to get us we have a 2 along this side, we have a root 5 as the hypotenuse, so our other leg is going to be a size 1, which is small. So this is smaller than 45 degrees, let's say. Right, because the long side is on the bottom, which means we're not going up as far, so therefore on the unit circle have to be below 45 degrees. Over here, same deal. We have a 3 along the x-axis. We have a 10 as root 10 as the hypotenuse, and so we find that we also get a 1 for the vertical side. Again, less than 45 degrees. That becomes relevant in a minute. When we take the arc cosine of each of these things, those are the individual sets that we get, but we don't know what the angle is. So that's going to be alpha plus beta. And the cosine of alpha plus beta is equal to, here we have the cosine alpha cosine beta minus sine alpha sine beta. And all I've done is I've moved the inverse cosine to the other side. So bring it over with the cosines and sines. Right, so that actually does belong here as well. Okay, so then we get the inverse cosine of cosine alpha we already had, that was 2 over root 5. Cosine beta we already had, that was 3 over root 10. Minus sines of each one. Well, we found out that the extra side was 1 in both cases. So here the opposite over hypotenuse for these respectively is going to be 1 over root 5, 1 over root 10. When we multiply those together in the appropriate amounts, we get 6 minus 1 over root 50. So that's going to be a 5 over root 50 that we're then taking the inverse cosine of. When we simplify the denominator, root 50 becomes 5 root 2. Our 5's divide out, and so we get the inverse cosine of 1 over root 2. Hey, I recognize that. Inverse cosine of 1 over root 2 is pi over 4, or 45 degrees. Since both of these things were less than 45 degrees, we can assume that they add up to 45 degrees. Now, it is theoretically possible that we could think of this and say, if these were sufficiently large angles, then their sum would add up to a number which was larger than just pi over 4 by itself. Could it be an entire rotation off? Right? So an entire rotation would end up being 9 pi's on 4. And the answer here is no, we can't have that. Right? Our angle simply isn't going to allow it. Adding them up to get something larger than one rotation just isn't going to be possible. All right, so we get pi over 4. All right. We made it to the Chapter 1 review. Woo! All right, Chapter 1 review questions. Gross. Find the sum of the roots of the equation. Root x minus 1 plus root 2x minus 1 is equal to x. Now this is a lovely example of what's called the P versus NP problem. What we have here is, this is telling us that we need to find the sum of the answers that are going to be for the question here. It's rather tricky, not terribly difficult or anything, to find the solutions to this equation. But once we find the answers, we have a list of x's that are acceptable. We find their sum, and then if we just look at the answer book, or look at the question book, our possible answers are 1, 2, 4, 5, or 6. Right? A, B, C, D, E. There's not really like a shortcut that we can take to just be like, is it going to be this one, and plug it in. Right? It's just not going to work for us. You can, however, take a couple of educated guesses and figure out whether any answers are going to work at all. So the number 1, for example, eliminates the first one entirely. Just becomes 0. And then the second one becomes 2 minus 1, which is 1, which is a perfect square. And that's going to be 0 plus 1 equals x, which was 1. So yes, 1's going to work. 2, we could go through this and just start guessing numbers. It's going to take a while. 2 is not going to give us a perfect square, so chances are it's not going to work overall. 3 isn't even on the list. 4, we could plug it in. We get root 3 plus, and again, something over there that's root 7. That's pretty nasty. So that's not going to get us 4. If you plug in 5, we get 5 minus 1 is 4. Root is 2 plus 5 times 2 is 10 minus 1 is 9. Take it square root is 3. 3 plus 2 is going to be 5, so that's also an answer. Right? And then 6 similarly is not going to work. So literally the answers are 1 and 5, and their sum is then going to be 6. So in theory, you could work this out if you just know a little bit about what's going on here. Since this is actually a math channel, right, then we want to actually solve this. So how do we do it? Okay, I'd said earlier, if we move the other one, 2x minus 1 here, and then we set this equal to x minus square root of x minus 1, and then square both sides. Then we get 2x minus 1 is equal to x squared minus 2x root x minus 1 plus x minus 1. Start rearranging stuff a bit. Try to get everything away from the square root itself. So we subtract x, we add 1, we subtract x squared, subtract x squared, subtract x, add 1. Negative x squared plus x is equal to negative 2x root x minus 1. Right, this is going to get us a negative x parentheses x minus 1, which is then equal to negative 2x root x minus 1. We could probably see that these are going to be square, one's a square of the other. So, can't really do much about it at the moment, but nonetheless might help you with some insight. Here, if we square both sides, we end up with x squared times x squared minus 2x plus 1 is equal to 4x squared times x minus 1. And in fact, right, we could multiply this all out. Alternatively, we can look at what else is going on here. If we divided by x squared, which is a thing people are wont to do, right? If x is not 0, then we can divide by x squared. Right? If x equals 0, then 0 equals 0, so that's true. So our candidate list is going to start with 0. Then if x is not 0, we can divide by x squared on both sides, and we end up with, again, x squared minus 2x plus 1 is equal to 4x minus 4. Right, move all that over. Minus 4x plus 4, minus 4x plus 4. X squared minus 6x plus 5 is equal to 0. And again, here, this is a simple job. X, this is going to be, they have to have like signs, and the bigger one is negative because of the negative that's in there. Like signs. So they're both negative. We have to have multiples of, or excuse me, we have to have factors of 5, so 1 and 5. They must add up to negative 6, which they do. X minus 1 times x minus 5 is 0, which allows us to then say that x could be 1 or 5. Yeah, right. Okay, then we should check these versus the original equation. So again, this is so we did check from above the 1 and the 5. So we know that these are good. We did not check 0. Mostly because we can't, right? If we plug 0 into here, we get 0 minus 1 underneath a square root, and we're trying to set this equal to 0. So over here, this is going to be 0 minus 1 as well. This is going to be I plus I equals 0, which we know for a fact is not true. All right, the reason that this works, not that it affects the sum anyway. So there's our E. Not that 0 affects our sum anyway, but it is not one of our actual zeros to the function, because when we plug it in, we get I plus I, which is 2I, not 0. So why does that happen? Well, we removed information from the equation. specifically whether that was a positive or a negative. It wasn't here. It was actually on this step. When we squared those negatives, it removed the information from above that told us whether this one here, up top, was a positive or a negative. And without that information, we end up getting, different equation entirely. But it could have been the difference of those two radicands, or excuse me, of those two radicals. And if it had been the difference of the two radicals, then we would have gotten 0 as a correct answer. And that also means that 1 and 5 would have been false. Pretty sure. Well, okay, 1 would still be true because plugging 1 in gets you a 0 on that term. Yeah, the 4 would not be correct. Or excuse me, the 5 would not be correct. So, 0 fails. So 1 plus 5 is going to get us 6, which is answer E. All right. Good idea. Okay, number 2. Determine the set of positive values. So therefore, x must be larger than 0. That satisfy the following inequality. 1 over x minus 1 over x minus 1 must be greater than 1 over x minus 2. So this is rational functions. We didn't really explicitly do this, but we did say that anytime you're faced with an inequality, maybe I didn't say this last, the stream when we did rational equations, but something I always tell my students is that if you can solve this as an equation, then you just have to have, that gives you the border points where the behaviors might change. That's it. So if we go through this and say, hey, I want to treat this as if it were an equation, right, we could put an asterisk on it. We can put quotes around it because it's not actually equal, but, we could pretend. Whatever we want to do. We now want to multiply all of this by the least common denominator, or least common multiple of the denominators for this equation. In that case, it is x minus 1, x minus 2. When we multiply by all three of them, one of them gets eliminated and the other two remain in the numerator. So x minus 1, x minus 2 minus x times x minus 2 and is equal to, allegedly, x times x minus 1. Right, if you want to know how exactly this works, all this stuff can be carried in to each of the ones, and therefore, since they're now part of those fractions, you can eliminate the one term that is common in both numerator and denominator. In the first one it's x, in the second one it's x minus 1, and in the third one it's x minus 2. Here we get an x squared minus 1x minus 2x, so therefore minus 3x, plus 2. minus x squared plus 2x is totally equal to x squared minus x. Let's see. This is going to subtract out our x squared here already. And then I would like to take this entire side and add x to it, because negative 3x plus 2x is negative 1x, and plus 2, so we subtract 2. Do that from both sides. Plus x minus 2. It's going to get us 0 is equal to, totally, x squared plus x minus x is 0 minus 2. Absolute value of x is going to be the square root of 2, and therefore x can be either plus or minus the square root of 2, where we get boundary points. Right, at these 2 points, we get that they are equal to each other on either side. And we could actually plug all that stuff in to try to make that work. That'd be pretty nasty with these being non-integer answers. And yeah. So when we do this, we end up with open circles on these. We need to be greater than, not greater than or equal to. So since we can't include the spaces where the equation is going to be 0, we have to find the places where it's greater than 0 only. So pick some test values. Let's try 0. Let's try, this is 1.414, give or take. So let's try 2 and negative 2. Right, so we go up to the original problem, and we say if we plug in 2, we're in trouble. I should have done that first. So, x cannot be, right, what's your domain? X cannot be 0, 1, or 2. If it is, you end up dividing by 0, blowing up the universe, all that good stuff. So, can't be 2. But it can be 3. You know what? I forgot something. Sorry. Let's go back. Where your least common multiple is equal to either, in this case, 0, 1, or 2, we end up with discontinuities. So these discontinuities also carry through to the end. And we say that, okay, you can't be at 0 or 1 or 2, which is really close to our square root of 2. Let's open this up a little bit. Okay. 0, 1, and 2 are where our function ceases to exist. So there's typically going to be some movement to a discontinuity here. So it's either going to jump up very high or jump down very high, reaching toward an asymptote. So, we need to guess particular numbers. Here I'd say like -2 is fine. Here -1 is fine. Here 0.5 is fine. Here this is a little bit more tricky. 1.2, 1.1, doesn't really matter. As long as it is before √2 or 1.414, etc. Somewhere between 1.414 and 2 would be something like 1.6, and then 3, outside of 2 entirely. When we pick these particular numbers, they tell us that all of the numbers within this region should have the same kind of behavior. So if we go over to, again, this is 1 over x plus 1 over x minus 1 is greater than 1 over x minus 2. So if we plug in -2, -1, -0, nope, positive. Positive 0.5, 1.2, 1.6, and 3. Alright, so 1 over x is going to be 1 over -2 plus 1 over -2 minus 1 is -3, greater than 1 over -2 minus 2 is -4. Can't do negative, oh no, -1's fine. This is 1 over -1 plus 1 over -1 minus 1 is -2. Here, 1 over -1 minus 2 is -3. Half is going to be 1 over a half is 2, plus 1 over -1/2 is going to be -2. That's nice and easy. Greater than 1 over a half minus 2 is -3/2, so it's 1 over that is -2/3. 1.2. Oh, lovely. 1 over 1.2 plus 1 over 0.2 is greater than 1 over 1.2 minus 2 is -0.8, which is 4/5. So 1 over that is going to be 5/4. Alright, 1.6 is 1 over 1.6 plus 1 over 0.6 is greater than 1 over negative -0.4. 3 makes it 1/3 plus 1 over 2 is greater than 1 over 3 minus 2 is 1. Okay, and the result. Negative a half plus negative a third is greater than negative 1/4. So a half plus a third is 5/6. So is negative 5/6 greater than negative 1/4? The answer is no there. Negative 1 plus negative 1/2 is negative 3/2 is greater than 1/-3. That's false. Okay, 2 plus negative 2 is 0, so that 0 is greater than negative 2/3, which is correct. 1/1.2 plus... Okay, so 0.2 is 1/5. Sorry. Reciprocal is going to be 5. 1/1.2 is going to be, what, 6/5? So 1 over that is 5/6. So 5/6 plus 5 is greater than a negative number. That is true. Again, positive plus positive is greater than negative. True. And then 3 makes this a third plus a half was 5/6 is greater than 1, which is false. So allegedly, should take all values between 0.5 is represented, so it's going to be between 0 and 1 exclusive. Between 1 and √2, all correct. And open at 2. All right. That's going to be it for tonight. So we'll finish out review for section 1 next time. And what do we got tonight? All right, let's head over to Rhaekodaclys, who is a person who has been working on well, let's see. I think he's a statistician and works on explaining scientific papers and stuff like that. Ooh. Is doing currently Your Brain on ChatGPT Review, and also has been doing a lot of games done quick type stuff for Final Fantasy V, I believe, is, if not his specialty, then one of them. So, hope you all have been having a good time. We'll see you on Friday for gaming type stuff. We're going to do Against the Storm and try and get that silver seal. Hopefully, we'll see how it goes. See you all later. My name's Obi-Wan Pez. This is N Simplex Pachinko. Later.